Swayam Prabha. Digital India. Educated India.
On the 20th lecture today, we are going to talk about a very important issue of error propagation in computing. And this is what we have talked about here as error dynamics and signal propagation. This is central to most of the computing methods, and we develop an alternative method or the correct method than that was proposed by von Neumann. And in this methodology, we are going to find out that in all computing, because of invoking of numerical dispersion relation, we end up having dispersion errors, phase errors, and this leads to what we call as the uncertainty principle of computing. We will show that it is only in the continuum limit we can perform absolutely correct computing. Anywhere else, we will have to accept some amount of error, and this is the essence of this new spectral theory of error propagation. Once again, we come back to discussion of Q waves for various discretization methods. We once again talk about the finite difference method, finite volume and finite element methods, and we pick up an example of propagation of a packet, and we also show what is known as a Gibbs phenomena. This arises whenever we have solution discontinuity, and from the foot or the shoulder of this discontinuity, we see downstream and upstream propagating small scale oscillations, and those are known as the Gibbs phenomena. And this is a major issue about compressible flow calculations, which have shock waves present, but nonetheless, we will not talk about it, but we should be aware of Gibbs phenomena as one of the major element of scientific computing. Having completed our discussion to some extent on parabolic equation and on the error propagation equation, we switch over to solving methodologies for elliptic equation. We notice that elliptic equations have characteristics which form conjugate pairs, and essentially that requires that the problem be treated as a boundary value problem or BVP. Even in solving this boundary value problem, we have two alternatives. Either we solve it directly, that would involve inverting very large dimensional matrix, which becomes prohibitive in most of the cases, and that is why we have to resort to the iterative methods. And once we start considering iterative methods, we have some interesting scientific possibilities. That is what we talk about by looking at the very basic equation, the Laplace's equation, identify its molecule, and we will see that this will amount to actually solving a linear algebraic equation with a pentadiagonal matrix, which are not banded together, and that is what would exclude the possibility of having an analytic solution for this pentadiagonal matrix, and we will have to resort to some iterative methods, and these iterative methods we will show is equivalent to invoking a pseudo time, and that has a very interesting consequence, because that pseudo time progression is related to the eigenvalue and eigen functions of that matrix upon discretization. Another issue of elliptic equation is basically the requirement of boundary conditions. Elliptic equations have complex conjugate characteristics. So, essentially if we have a elliptic equation of order 2n, we would require n boundary conditions. So, we are going to discuss quite a bit about this boundary condition requirements of elliptic PDEs. Well, let me begin. Today we wish to basically talk about a related topic that we had started discussing in the last few lectures. This relates again to the spectral analysis, and we want to talk about a very important issue which was considered very significant, and it is still considered very significant. It relates to understanding of phenomena as to how error propagates. You see, the whole thing about numerical computation is about how do you control error, because accuracy is the main concern. We do not want error to hurt our numerical activity. So, we basically start off with the same model equation that we have been looking at. This has got certain features which we are all now familiar with. So, if this is our basic equation, point of reference to study error propagation, then let us first define what constitutes error. Error would be defined as the exact solution minus the numerical solution. Okay? The subscript n refers to numerical solution, and we have also noted in the last few lectures that the numerical solution for this particular equation would be determined by the initial spectrum as given by A naught k, and the method that we choose would have its numerical amplification factor g. So, if I take its modulus and suppose we arrive at time t after n such steps of delta t, then this g would be raised to the power that n, or alternatively we can write it as t over delta t. And each step of time evolution gives rise to a phase shift that we called earlier as the beta j, if you recall, and then when I sum up all those phase shift, that accounts for this numerical phase speed that we called as C of n. And we correctly identified the numerical dispersion relation, which we show it by the subscript n, which shows that numerical circular frequency is equal to the wave number times the numerical phase speed. And one of the important finding that we have focused upon is the fact that this numerical phase speed is not equal to c. And not only that, it is not equal to c, but also the fact that it is not a constant even. See, the physical phase speed is a constant, c is a constant, but C n, as we have noted, that it is going to be a function of k, and this leads to the dependence of C on k, and that in turn relates to numerical dispersion, and that is why the sobriquet here is that this is a numerical dispersion relation. Now, having accepted that expression for numerical solution as a consequence of the adopted numerical method, we can actually look at what this partial derivatives of the numerical solution with respect to x and t amounts to. It is rather simple. Taking a x derivative would be simply multiplying by I k. So, we are assuming that we are not making any dispersion, any error in evaluating the derivative, right. I am not writing I k equivalent, I am writing the best possible scenario, that is using a spectral method. If I use a spectral method in calculating this derivative, I will just simply take the Fourier amplitude multiply by I k. If I start talking about a particular method, then I will replace this I k by I k equivalent. That I suppose all of us appreciate. Okay. Once I evaluate that derivative the best possible way as given here in equation 4, next you could do is evaluate the time derivative of the numerical solution, and because time appears in two places, one is of course in the phase definition here, another is mod g to the power t by delta t. So, we get two sets of terms, right. Now, this is where I think we should allow ourselves to digress little bit into history. This is related to the Manhattan Project. All these big guns of US science were in New Mexico trying to develop the nuclear bomb, and one of the showman was John von Neumann. Well, as a Hungarian, he used to go by various names. In America, he was John. To his friend, he was Johann. So, John was the guiding spirit behind computing activity at Los Alamos. So, in developing, of course, he was also associated with the advanced science at Princeton, that big group which were involved in numerical weather prediction. So, they had multifarious interests, really polymath people. I mean, let us all tip our hat to them. They are real geniuses, probably the last bunch of geniuses got together in one place, that must be Los Alamos. And there von Neumann was looking at computing, and he came out with this observation, which seems very, very intuitive and acceptable to all of us even today, is that if I am looking at a linear system, and if I am trying to compute a linear system, then it is natural for us to accept the error committed also would be given by a linear system. It is so common sense thing for us to accept as the way we are trained in mathematics and physics all the time. So, if that is the case, my governing equation is this. If this is my governing equation, what would I expect? The error should satisfy this, right. The error should satisfy this, right. It took us almost 60 years to figure out that this is not correct. And that is what I sent you the link for the paper that you could download, which we actually came out with in 2007. How do we come to that conclusion? Let us go through the steps slowly. So, E has been defined as departure of the exact solution from the numerical solution. So, I just simply replaced E by U minus U n. And then of course, you see it leads us to two sets of terms. What about the first two terms? By definition, that is 0. So, what I find that the error dynamics is not homogeneous like what we expected, the right hand side equal to 0, but it is determined by this quantity, right, how the numerical solution is going to be. It is such a simple observation. Now, if that is so, what I could do is I could write, it is just simple jugglery here. I have added and subtracted this term, so that we have del u n del t minus c del u n del x. These two are going to cancel each other. So, basically then a little bit of reorganization would tell us that we have a inhomogeneous equation. The first part relates to what we do numerically, and now you notice that I have purposely replaced c by c n, because that is what we are playing with. And then in addition we have this term. Since we have already evaluated this temporal and the spatial derivatives, we can put them in and collate. So, we are going to get these three sets of terms. Well, it is easy for you to understand that this comes from the x derivative, the next two terms come from the time derivative, right. So, we then substitute this, and this is what we get. Now, what we did, of course, in the previous slide, I could see that here Cn is inside the integral, here the Cn is outside the integral, right. So, what I could do is I could integrate this by parts, right, because Cn and the other thing is also function of k. So, I do that and then I would be able to cancel out this term. However, in the process of that cancellation, what happens is we get this dC and dk term. You see, this is something we have noticed just a while ago, that Cn is not a constant, it is a function of k. So, that is what we sourced it as the dispersion error. So, dispersion error directly appears in this set of terms, and this of course comes from the time derivative term, and you can now see what I have been shouting hoarse for last few lectures, that why we must have neutral stability. Now, do you see what I mean by having a neutral stability means? If I have a neutral stable method, then what happens to mod g is 1, ln g is 0. So, you do not accumulate any error if you have a neutrally stable method. So, what happens is you substitute all of this and you get these 3 sets of terms. This is what we get. That is such a simple common sense observation. So, what we could do is we could club this 3 terms and identify them. What I find that the error dynamics is driven by 3 sources of terms, and this is something that we are not talking about any specific method being chosen. This is a generic causes, right. This is the disease of numerical computing. So, whenever we do numerical computing, we are going to suffer by these 3 sets of terms. The first set of term is pretty much obvious, because this relates to phase speed. So, we call it as phase error, and what you also notice that this phase error term actually depends upon the smoothness of your actual solution, numerical solution. If the problem that you are solving, that solution is discontinuous, that means this derivative is large, del del x of u n, then of course, this is going to hurt you. But if I have a very smooth function where this quantity itself is small, you may not see its effect very much. So, this phase error is something that you are going to see what we talked about when we started talking about ODEs. You recall we talked about that, that is part of your first assignment also. You saw that whenever you have large gradients, solution gradients, you have to be able to resolve it, and this equation and this term tells you those kind of gradients actually contribute a lot to the error. So, that is that part. The second part is pretty much obvious. We call it dispersion error because of this term dC and dk. I have not done it, I will leave it to you for to work out. Show this to be equal to proportional to Vgn minus Cn. Okay. So, you should be able to show that this term is given by the departure of the numerical group velocity from the numerical phase speed. If you are looking at the original physical problem, both of them are the same, right, Vg equal to C. So, you do not have it. So, you can see that this term is identically 0 for exact solution, because Vg equal to C, it is a non-dispersive system. But in this case what happens is we found out Cn is a function of k, that is why this is non-zero, and that is caused by this, the departure between the group numerical group velocity from the numerical phase speed, okay, scaled by of course, the wave number k itself. So, this is the second source of error that you would be concerned with, and the third one is what we have been repeating time and again, that look, if you have anything other than neutral stability, it is going to contribute to the error. Okay. So, actually you can see that this analysis or this result that is projected in front of you would be colored by the choice of your method. You know, if I now focus upon a particular method, I should be able to figure out what these each quantities are, and then I can figure out what is the actual error for that particular method is. But this is a most generic description of what we get to see. So, I think this is what I have put it as a summary, that of course, the von Neumann stability and error analysis is wrong. Unfortunately, this is what you find in all textbooks, even including the book that I had written in 2002 or 3. We assumed it is so intuitive for us to accept that the linear dynamics should follow that. We also fell into the same trap. However, we have shown here that error is driven by the following 3 sources of error: the phase error, the dispersion error, and error due to stability or instability. And this component is of course 0 for neutrally stable algorithm. This is a question that we should ask ourselves: can we really get rid of phase and dispersion error? I have a pessimistic message for all of you: no. And that is what we coined this term. It is the uncertainty principle of computing. Whenever you compute, you cannot ever assure that you can take care of these, until and unless you have a perfectly periodic problem and you can adopt a spectral method. So, what happens is most of the practical problems would not let you use spectral method, and then you come to this pessimistic conclusion that we cannot perform completely error free computations. It is only possible, of course, when you go to the origin of that point KH-NC plane, where everything is perfectly kosher and nice. So, that would imply that you will have to take delta x vanishingly small, so that you are going to the continuum limit of k delta x going to 0 and omega delta t going to 0. So, this is what we have seen. Okay. Now, I did talk about this part G and VG for these 4 classes of methods. We picked up from little advanced finite difference calculation. This is a classical finite difference calculation. This is some finite volume calculation, and this is a finite element calculation. And I brought to your attention the existence of this line VGN by C equal to 0, above which you will see the VGN by C is negative. And these components of error or the solution, we will call them as Q waves, and they are again spurious. They do not belong physically, they are attributes of the numerics, and these are the solution components which actually have negative group velocity. They are opposite of the physical group velocity, and for 1D wave equation 0 is that demarcation line. And we can actually then catalog what happens to this Q wave business. Now, I purposely projected this in our K equivalent by K solution in versus KH plane, and this is the real part and this is the imaginary part. The real part we know determines the phase of the solution. The imaginary part tells us whether we are adding a numerical dissipation or anti-diffusion, right. Now, on these 2 frames, we have identified locations, the values of KH above which for that particular method actually has Q waves. Okay. And you can see that the most recent and most successful finite difference method that some of us use gives you the highest Q wave limit, that is roughly around 2.4. So, even with the best possible methods we are having today, what we notice that any KH component above 2.4 have this unphysical attribute where the solution will propagate upstream, and this has got nothing to do with physics. This is totally a numerical error, right. Whereas, if you come to your CD2 method, which is the lowest possible curve, that happens at pi by 2. So, at least by going from the classical CD2 to the best possible method that we have, we could actually raise that limit from 1.57 to about 2.4. So, that is something. Now, despite that, how come people have not located and reported Q waves before? Well, two things. Two things are, you see, even at that range, what happens? What does this real part do? Ideally, anything above this is severely attenuated. Even at that point, this attenuation is roughly about 45%. So, every time step, if I adopt a CD2 method, I am actually attenuating the signal by this amount, right. So, that is about 45%. In addition to that, of course, the CD2 method does not have any numerical dissipation. So, that is why you have it flat equal to 0, right. However, this 45% attenuation itself will remove that quite effectively. You know, if some quiescent Q waves are created for values of KH above this, they are severely attenuated because of this filtering attribute of this discretization methods, right. Whereas, if you take this good method, which actually takes this limit from pi by 2 to 2.4, you can see this part is attenuated by only 3 or 4%. So, this is what I was jokingly saying, that sometimes your strength becomes your liability, right. You have a better method, but that is why you get to see the Q waves, and you choose a bad method, you will not see it, and those people will come and commiserate with you, saying that, oh, bad luck, you should try better methods. So, this is a very, very interesting observation. However, I must also point out that some of these other methods, the finite volume, finite element, and this better finite difference method, we do add numerical dissipation, okay? And you can see what happens. For example, this finite element method drawn by this blue line, this is the Q wave limit, and that is where we are adding this much of dissipation also, more than 0.5. So, what happens is those people who will be doing finite element method, they will say, oh, this is a figment of your imagination, because we never see it. But they do not see it, because they add so much of numerical dissipation that they damp out those components, spurious components, unknowingly. If they would have done it knowingly, I would have really acknowledged that. They probably do not even know what is Q waves. Anyway, that is different. Now, this is the summary sheet for trying to solve the problem. So, basically, once you know what the problem is, you can set up critical tests, right. So, what we found out that for the CD2 method, the demarcation feature was pi by 2. If I now take a wave packet with a KH greater than pi by 2, then what will happen to CD2 method solution? The whole wave packet will go in the opposite direction, right. You have, so that is one thing, and what we have done is we have chosen a wave packet with KH equal to 1.7 purposely to test out all these 4 methods. So, this is the value of KH equal to 1.7, and we have taken quite a moderate value of NC. Now, what happens is, let us solve this and show the exact solution by the green lines. this is the green wave packet is the exact solution, which is going to the right, because we have taken I think c equal to 1. So, the solution is going. So, between this peak you can see the difference is about 0.2 here, and it keeps increasing. Now, the CD2 method, what it does, it actually sends the whole packet to the wrong direction, and that is what you are seeing, and it is a non-dissipative method. So, it does not dissipate, right. So, you retain the identity of the packet, but it makes it go in the opposite direction. This is the method that we will be talking about in this class. This is what we have developed ourselves, and you cannot distinguish between the exact and the numerical solution. They are going together hand in hand. Of course, our method also will fail if we choose a value of k greater than 2.4. So, we have to be very careful in what conclusion we draw. Now, for the same problem though, if I use this finite volume, this is the finite element method, streamwise upwind Petrov Galerkin method, SUPG, and look at the solution that is shown. It is 0.004 and 0.012, and you can see the green signal and the red signal. The times are so low that you do not even see their convection, right, but you can certainly see the effect of numerical dissipation. See, the solution is virtually diminishing there, and this is the corresponding commercial software type of method like Fluent. Fluent will do this with their best method. This solution is again shown at 0.008 and this is 0.1, and you can see the signal has disappeared. It has all become quiet. That is what I say. It is a quiet of the battlefield. Okay, so you want to see it a little more graphically, and this is what it is. You can see an animation. The top one is your exact solution. The middle one is what we have carefully crafted, and you can see this classical CD2 method. The whole packet is going to the left instead of going to the right. So, I suppose you appreciate now. So, what is Q wave then? Q wave is nothing but an extreme manifestation of dispersion effect, because that is what we got. It is a property related to Vg, and this Vg is so bad that it actually takes you in the opposite direction. So, Q wave is nothing but the extreme manifestation of dispersion error, and the next thing that I am trying to show you is we have just now seen what happens to because of dispersion error. How about the phase error? To understand what phase error does, we have again purposely designed a case where NC has been chosen in such a way that I have G equal to 1. I have chosen a method here for which this G is almost equal to 1. So, what happens here? We are trying to study the solution of this equation for a function whose initial condition is given like this. So, it has a ramp like this. So, there is a slope discontinuity here and there. Recall that phase error depends on del del x of u n. So, if I set up a problem where I purposely have a slope discontinuity, I should be able to see its effect, right. Now, these are the corresponding properties of the so called accurate method that we have developed ourselves, that optimum scheme, and these are some of the data which has been highlighted by Yogesh here for you to view, that if I choose a kh equal to 1.7 and NC equal to 1.3. So, we are purposely doing a very large time step calculation, NC equal to 1.3. And you can see now what happens when I have a solution like this. So, this is not solving a wave or wave packet. This is what? This is not really monochromatic event. This is a real true polychromatic phenomena that you are seeing, because I have this u versus x, I can do the Fourier transform and I will see the whole range of k is excited. So, there is nothing that you can synthetically pick out one value of kh. So, this whole range of kh are coming into play here, right. So, you have to remember that this is not like the previous case, where for the wave packet we chose kh equal to 1.7. For this problem you do not have that luxury, the whole range of kh has been excited. Now, if you solve this, well, the ramp actually propagates to the right, and I have taken the ramp angle is less than 90 degree. So, it is about 0.45 pi, and what happens is at the foot and at the shoulder, because the slope discontinuity, I pick up error, and that error has been plotted here, and they have been plotted at a very early time. This is about 3 delta t, this is at 6 delta t. So, it is just the story has begun. I have this error, I can do a Fourier transform and I can plot it, and this is what I get. The Fourier transform, the amplitude, Fourier amplitude versus kh have been plotted, and I get this type of footprint. Now, what we find that the error seems to have two maxima. One corresponds to a little higher wave number, which I marked by A, and one corresponds to a little lower value. As I have identified to you that you can download the paper, if you do, you will notice what really happens and why we are seeing this. What are those 2 points A and B refer to? What is the source of those errors? Well, what we could do is, for the chosen value of n c, I could plot mod g, and let us say I have some value of g mod g equal to 1, and then what we find that we are going to get the different values of g for different points. So, we are going to see something like this. So, some cases the error would even be going higher. So, this could be, say, j equal to some the middle point I am talking about. So, you can get this. In fact, if you look at the second point, if I have a first point here and if I look at the second point, I find that this mod g actually goes like this, and you know why, because the second point information has been brought in from upstream, and that gives rise to a large source of error. So, this peak where g is greater than 1, this point corresponds to E, because that is where you get more than 1 and you get that. So, that is what you are seeing, that with time this peak in A is actually progressively increasing. That is one thing that you notice. In addition, if you have noticed that error evolution equation, we have a component which is proportional to 1 minus C n by C, and that I could plot versus k h. And what is found, that if this value is 0 here, so for most of the points this remains 0, but then at one point it actually comes down and bursts upon you like this. This point corresponds to B. So, what happens is, this quantity remains benign for the whole range of k h, but for a particular value of k h it actually has a very sharp maximum, and that maximum actually gives rise to this second peak, and that also keeps growing. If you look at this kind of a feature of the solution near discontinuity, where solutions have overshoot and undershoot. This is what is called as Gibbs phenomena. There are lots of myth in the literature about Gibbs phenomena. This is the same Gibbs which you may have come across in chemistry, thermodynamics. He was a very, very prolific gentleman, and do you know he was the first professor of engineering at Yale with a salary of $1. It was more an honor than a salary, right. So, Gibbs actually noted this, and this is called as a Gibbs phenomena, and there are lots of myths, but now you can see you have an explanation what causes Gibbs phenomena, right. That comes out from this term. So, you can understand well whether it is numerical or not, this is the driver term for Gibbs phenomena. Of course, you will have to find out this undershoot and overshoot looks like a wave, right, and when they do look like a wave, they also behave like a wave, they move, and you got to find out what is the direction of propagation of those waves by looking at the corresponding VG plots. So, you might see sometimes it will progressively only go in one direction and not in the other direction. In this case, you know, you can look at the paper and you will see that if I increase this ramp angle, I will make this thing worse, right. So, that also tells you this role of this term. So, if this term is made more adverse, you are going to see more error, and this problem is not academic, because this is truly a problem of engineering dimension, because if you are an aerospace engineer, you know you do get shock waves. There the solution actually jumps like this, the pressure, the velocities, they jump like this. If you are designing a traffic system, you can come across this traffic bottleneck, that is where also you get solution discontinuity or hydraulic jump. And we talked about other things of sonic boom, etc. They all suffer from this issue of Gibbs phenomena. Okay. So, I think I wanted you to know about this, what this is. Maybe it is time that we should do a non-numerical home assignment. So, I would ask you to go back and write out the error evolution equation for the heat equation. We have done it here for 1D convection equation. So, you do it for the heat equation. I will send out a email, so that those who are not here, they do not have an excuse for not submitting. So, everybody will get a chance to submit, okay, and get appropriate credit. Okay. So, we will now go somewhere else. I get the feeling that we are going slightly slowly than what I would have, but at the same time I want to be with the whole class. So, please do interrupt me if you do not follow any of the things that I am saying here. These are some of the things you will not find in any book. These are not some of the things which you have ourselves not written completely. So, as we go along, I keep narrating things to you. So, feel free to interrupt me any point in time, but let us go back and see. This is a parallel track of development of CFD computing. People have been solving heat equation, parabolic equation. People have been also solving elliptic equations. These are the two major preoccupation of people maybe 100 years ago. And lots of the things belongs to the realm of theory, and you understand what their ramifications are. We have noted if we are looking at quasi-linear partial differential equations, and if they happen to be elliptic PDEs, we have complex characteristics that renders them as a boundary value problem, and the reason is that you do not have real characteristics. So, information does not necessarily have a directionality, that it is approaching that point from one particular direction. It means that it can appear from everywhere. So, this sort of feature that you do not have a specific preferred direction makes it omnidirectional, right. So, every point is affected by every other point in its neighborhood, and those points are eventually influenced by their neighborhood, and in the end you hit the boundary. That is why these are called boundary value problem, because everything is in the end determined by the boundary conditions and nothing else. Okay. That is what we have written here. Now, that also actually puts in a damper in all our activity. That means that if I am trying to solve elliptic PDE, unlike parabolic PDEs, where we knew that information propagates along t equal to constant, like in the heat equation, and I could solve one timeline at a time and I can go forward, right. So, that makes the job lot more simpler, but because this is a boundary value problem, you will have to take the whole domain together, make the job little more involved. That is what it is. You have to solve the whole problem over the complete computational domain, and after you have done that, you end up with the same thing, A x equal to b. And depending on whether you are choosing a very structured discretization or an unstructured discretization, this A can have all kinds of features, right. For example, when we adopted that implicit method for heat equation, we saw that A happened to be a tridiagonal matrix, right. And if it was a periodic problem, we had periodic tridiagonal matrix. What happens to elliptic equations? Well, we can have different natures of A. We will talk about few very simple cases, but this is what we also know, that to solve A x equal to b by direct inversion, we would require n cube calculations, and that is prohibitively expensive, very bad thing to encounter. So, what we do is we circumvent the problem. Historically, this has been done ever since the time of Jacobi, that you try to use iterative methods. So, you make some kind of initial guess, and then you keep on improving the guess based on some algorithm or methods. Okay. Now, if we do that, the main question that remains, we have started solving a problem which has elliptic nature. Now, the moment I choose on an algorithm, I have picked the problem, I have changed the problem. So, I could work out what is the equivalent equation is. That is what you did in your midsem, and you found out that you solved something else, right. So, this should alert us. We should not panic and give up, but we should find out what it does. For example, solving this Laplace's equation in a Cartesian grid with uniform spacing in both directions, this amounts to this. This is a very interesting observation, that u I j is nothing but the average of its 4 neighbors, right. And what does it indicate? If I am trying to solve, let us say, the Laplace's equation in a domain, where would I get the maximum value of the solution? Can it be in the middle? It has to be only at the boundaries. Why? Because interior points are nothing but averages. Average cannot be more than the constituents, right. It is a simple observation. So, that is the maximum principle of Laplace's equation. Please do not confuse. I have seen places where people keep saying that this maximum principle is true for all elliptic equations or even for Poisson equation. It is not true. Poisson equation is where you have a right hand side, right. So, if you have something on the right hand side, this logic goes out through the window. So, do not try to do this, but at the same time if you are solving a Laplace's equation and in the process of your solution, if you see somewhere in the middle of the domain solution is becoming larger, you know already you should stop and go back to the drawing board and see whether your code is right. Okay. Now, let us also make our life easier by considering boundary conditions given as Dirichlet conditions. Then we will have to be solving problems for I equal to 2 to n minus 1 and j equal to 2 to m minus 1. And now, for this problem, as we have written in 3, we get this structure of the matrix. The A matrix looks like this. The diagonal term comes from that 4 u I j, the minus sign, and then you have one point to the left, one point to the right coming from the x derivatives. And please be aware of the fact that if I do not say anything specifically, we are always going through this. So, if I talk about this x or let us say I or m index, and if I talk about y or n index, we will be identifying a domain and then we will be following this sequence from left to right and from bottom to top. This is what is called as a lexicographic pattern. What is lexicographic pattern? That is what you do in reading books, lexicon, right. Different languages have different way, but they still do have the structure, right. So, either you start from left to right and from bottom to top, that is how we read books. Here we are going to follow this from left to right and bottom to top. Imagine if the books were to be written in this fashion, all of us would take some time getting used to, right, reading from the last line and going from the top of the page. But anyway, in computing that is what we do, and you can see then if I am looking at one particular point here, then I need 4 neighbors, right. So, this point gives me that minus 4, the diagonal entry, okay. And this point and this point, because we are going from left to right, so they have a contiguity, right, they follow each other, and those are the ones that you are seeing here, plus 1 here and a plus 1 there, okay. Now, this is really the neighboring points, okay. What about this? This point is happened a pitch before, so that is this. Those are these entries which are corresponding to j minus 1, and j plus 1 would be given by this diagonal entries. So, these are once again called pentadiagonal matrix because you have 5 diagonals, but they are not packed together. If they were packed together, if these 2 lines, this diagonal and that diagonal were sitting next to those other 3, life would have been lot more simpler, because like Thomas algorithm we should be able to write out a exact solution procedure. But unfortunately, because of this intervening zeros, this is one of the vexing problem that has baffled applied mathematicians for a long time. So, we cannot directly invert this matrix, although it is sparse, right. So, this is something we should keep in mind, that this direct inversion is not possible. and if the size of the matrix is large and if we are trying to do a direct inversion, we are going to take very large computing time at every time we have to solve that equation. And in actual physical problem, it may so happen that for a time dependent problem, you will have to solve a elliptic equation at every time step. So, you can imagine that any time saved for each time step accumulates and saves you lots and lots of computing time. So, there is a incentive for us to look for methods which will allow us to solve this equation in an efficient manner. Now, that was the motivation behind developing various approximate means, and let me start with the oldest and the classical method due to Jacobi. Later on Richardson also used the same method, maybe he popularized, so it is also called the Richardson method. And what we do here, let us say we are solving that Laplace's equation with unequal delta x and delta y given by h and k. This is the discrete equation. And what you do here in the Jacobi method is you try to evaluate the solution by pegging the diagonal entry at the current level and everything else at the previous level, right. So, this actually was practiced with the hope that if I take a very large number of steps when n goes to infinity, then the solution would not know what is the difference between n and n plus 1. So, initially it all got started there, but then subsequently people went through the analysis and tried to justify why and how this method would work. And you have seen it yourself in your exam paper that you actually are doing something like this, because when I am writing this shifting this index superscript by one level, that is equivalent to doing this, right. I am introducing some kind of a pseudo time stepping. And if I substitute this in the prior equation with non-uniform delta x, I mean they are uniform in x direction, they are uniform in the y direction, but delta x is not equal to delta y. Okay. So, then we get this equation 6, this alpha multiplicative constant depends on the time step times the space steps that we take. And this we have done it. So, I do not think I need to explain it to you to that extent. Only thing is, you note that in 8 and 9 we do not write u x t and u y t. The reason is obvious. We do not want to increase the order of the system, because u t itself is Laplacian. So, if I take u x t, that would be actually increasing the order of the equation. So, anyway, we figured it out, we got the solutions, these auxiliary equations collated with the differential equation gave us the characteristic determinant in terms of equation 10, and you can see one of the characteristics of course is t equal to constant, that tells you that you are basically marching in time. So, that is your parabolic direction, and in the space direction we have seen, let us say dy dx as a pair of this. Please do understand that all elliptic equations have to be of even order, because if you are going to get complex characteristics, they have to be conjugates, right. So, always elliptic equations will be of order 2n, right. That is what I noted down here on top, that elliptic PDEs are of order 2n. Now, this is a very interesting observation. The next line, the number of boundary conditions, this is something I find very baffling. So, I just drew two diagrams here below. Think about it. One is a perfect rectangle, another is a rectangle, but with corners rounded off, and you come back and tell me how many boundary conditions we need in the next class. Okay? We will stop there.